All right, so we got the recorder turned on, and since somebody said you'll use handwriting, I'm gonna do it that way. It's under Accessories, Zerno, and maximize the screen. And then we go to all files. All right. There we go. Yes. I believe so. Yeah, it's recording, and I'll just double check on the voice part. Yep. So we're good. All right. So this is for a practice test for the second exam, which is on next Wednesday, not next Monday. So that gives you guys 2 class sessions to ask questions about the material, which is good, okay? The location obviously is not going to be 407. This is from the past semester. But in terms of the other parts of this, it's still applicable. So open material printed or handwritten prior to the test, that part is still applicable. Oh, we got chairs. Extra chairs. We'll take some. Okay. Hi, thank you. All right. So getting back to, you can just put it next to the door. When students come in, maybe over here. Yeah. Yeah, when students come in, I'll just ask them to take these. Yep. Okay. So it's kind of the same thing as last time. You have it's open material as long as it's printed or handwritten prior to the test. And then the rest of this is pretty much the same as your exam 1. The second exam also only accounts for 20% of your final grade. So the proportion is the same as exam 1. Exam 2 and exam 1 have the same proportions. So I think we should be good now. Yeah, thank you. 5 is good because I got 5 more back there. But thank you. Yep. All right, so moving on to question number 1. So question number 1 is your CNF type of homework assignment, question. So the first thing we need to do is to express psi as a conjunctive normal form, okay? This one is a lot easier. Your homework assignment has one of the more difficult ones. So this one is easier, but we still want to kind of go through the whole process to do it. And let me see, because I need to do some cable management now. Okay, there we go. And let's see. Okay, there we go. It's kind of interesting to have a podium. I haven't used the podium for a long time. Okay. All right, so the first thing we need to do is to convert psi into a PDF. So I'm going to use the shorthand. So in the test, you can use these shorthand too. So we have not P or not Q, and then the whole thing implies R. So we want to convert it into a CNF. So the first thing I do typically is to get rid of the implication. So what we do is we use the definition of implication. So we use the implication here. So now we have the negation of the first part, which is not P or not Q. And then we have an or, the second part, which is just R by itself. Do we have any questions about getting rid of the implication? Is that good? All right. So if we are running out of chairs, just go ahead and pull a chair. Yep. Yeah, it might be a little difficult for you to write notes. Sorry about that. All right, so then the next thing we want to do is to use Demorgan's law to basically move the negation on top of the OR, which is this part here, into the OR. Okay. So that involves the negation of P, the negation of the negation of P, and the negation of the negation of Q. Okay, that's the result of Demorgan's law, or the one application of Demorgan's law, and then plus R, which is OR R, right? So we can now do some simplification because not is canceling itself out. So we now have P and Q or R. It is not in CNF because if it were in CNF, then we would not have the OR on top of the AND. So we want it to be exactly the opposite, which means we can use distribution in this case. So now we have P or R and Q or R. So that becomes the CNF of psi. Do we have any questions about the first part? Are we good? Okay. So the second part is the proposed theorem. In this case, is the more difficult one. So the proposed theorem, which is phi 0, is Q implies P or not P and Q and R. Okay. So now we have to convert the negation of that into a CNF. Okay. So we are not converting phi 0 itself into a CNF. We're converting the negation of phi 0 into a CNF. So we'll write it over here. So we'll say the negation of phi 0 is going to be the negation of that entire thing. So we got P implies Q implies P, or not P and Q and R. Okay. So in this case, I could do the Demorgan's law first, but I just do not like to look at implication, so we'll take care of the implication first. So we'll keep the overall negation on the outside, and then we convert Q implies P into not Q or P, and then we have another OR here, and then we have the same thing, not P and Q and R, like so. Do we have any questions about this step? Are we good? Okay. So the next step is we can lose the parentheses. We can dissolve, this parentheses here because we have OR and OR here, so they can be one big OR. So the conversion just looks a little bit easier that way. So we have now not Q or P, or not P and R and not P and Q and R. Okay, there we go. Is that okay? So that's just using the associative law to get rid of the extra parentheses that is not needed in this case. So now finally we can apply Demorgan's law. So Demorgan's law is going to distribute this negation into the inside of the OR and turn all the ORs into ANDs, which is actually advantageous to us. So we'll see what happens here. So we get not Q, right? And not P, and the negation of not P and Q and R. So close that, and close the whole thing. There we go. Are we good so far? Okay. So not Q is really just Q itself. Okay. Not P, it's fine. Just let it sit by itself. So now we have to apply Demorgan's law again because we have this negation of a conjunction. So apply Demorgan's law again, and then we end up with not Q, not P, and then we have to change the conjunction into a disjunction. So we have an or, not Q, or not R. Are we doing okay so far? Okay. And we have one extra step to do at this point, which is to get rid of the not. So we have Q and not P and P or not Q or not R. And that becomes another CNF. Are we good so far? Do we understand why this is a CNF? Yeah. Good. All right. So the proof using resolution is to combine the two CNFs. So now we combine the two, and we have P or R and Q or R. This is coming from psi, okay? So this part is psi. And then we merge it with the CNF of the negated phi 0. So we got Q, we got not P, and then we have P or not Q or not R. So at this point, we can try to apply resolution. And we try to apply resolution to the point where we can no longer get new terms, or we get to the zero, which is contradiction. So we're going to stop one way or another. So this part here is what we know as the negation of phi 0. Okay, so now it's basically just resolution. All right. So the way we apply resolution is we look for the same term. One side is negated, the other side is not negated. So we can see that P, this not P, can combine with this P here, and then we just get R back. Okay. So I'm just going to use a graphical way to represent it, which you can also do in the test, because that can save you a lot of writing. So we just say that this combined with that will give us just R by itself. Are we good? So with this R, we can combine that with this term here. So we get P or not Q. Is that okay? So P or not Q, with this P, we can get rid of that P too. So we have, now we just have not Q left. So I'm just looking for Q, which is from here. We got contradiction. This may not be necessarily the shortest route to get to a contradiction, but it is one way to get to contradiction. So your score is not going to depend on whether you give me the quickest and fastest way to get to a contradiction. You just need to show me that you know how resolution works, and you know when to stop. And on top of that, you have to show me that you know how to interpret this contradiction. So now you have to say, because it has a contradiction, because psi and not phi 0 implies a contradiction, phi 0 is a theorem. So you have to make that conclusion, okay? So mechanically, if you do all the derivation correctly, you'll get partial credit. But in order to get full credit for this particular exam, for this question, you have to make a conclusion and say that contradiction is what allows us to make a conclusion and say that phi 0 is a theorem of psi. Yep?
So not P can be used to cancel out more than once?
Yes. Okay. Yep. So all those terms can be used as many times as you see fit. Yep.
You have right after it says because psi and not phi 0
implies
false.
Implies false. Yeah, that's a 0.
And then it says after that not phi.
Yeah, this is a phi 0.
Should that be not or just?
Oh, right. Okay. You're right. It should be just phi 0.
Okay.
Yep, without the not. Yep, you got me. There we go. Good job. So are we good so far? So this means, you have to remember how to convert a general Boolean expression into a CNF. You have to remember that it is not the theorem that we want to prove that you have to turn into a CNF. It is the negated version of that theorem that you have to turn into a CNF. you have to remember that you have to combine those two with a conjunction. So there's a hidden conjunction between these two. And then you have to remember the mechanism of resolution. And then do it step by step until either you can no longer derive new terms or you arrive to a contradiction. Yep. Question?
Can I write like the or falses and the and trues?
Yeah.
Single time?
Yeah, you can do that. So the question is, can we add, or false here, or false here? And the answer is yes. It is just kind of implied without writing it out. Yep.
This is kind of off topic, but I'm just like thinking these chairs are a lot more comfortable than those ones in there. Can we stay in this room? if possible?
So now we want to stay in this room.
Just take all the chairs from this one and put them in the other.
It'll be funny to put those chairs into this room because now we cannot use the lab benches.
Just a thought. I don't know if anyone else agrees, but
Okay.
I definitely think these chairs are comfortable.
Okay. Well, that's because we have a lot of people not showing up because the roster still shows 49 as enrollment, and this classroom only has enough chairs for 31. Yeah. Yeah. Okay. That room is definitely useful for test days. Yes.
We could just get that room for test days.
Well, it's only today and Wednesday that they will need that room. Okay. All right. Second question. Question 2 of 5, and I'm going to make all of these questions carry equal weight again. So it's easier for you guys to evaluate, which one to answer first. You just pick the easiest one or the one that seems the easiest to you. Okay, so this is question 2 of 5. In the old days of modems, text data is often transmitted using 7 bits of data and 1 bit of parity. So if you don't know what a parity is, it's okay. It's explained next to it. A parity bit is essentially a modulus 2 sum of the data bits. So you just add up all the data bits and you mod it with 2, and that's basically what the parity bit is. The problem with this approach is any even number of error bits out of the 8 bits, because we're combining the 7 for the data and 1 bit for the parity, cannot be detected because they cancel each other out. Okay? Huh?
I'm not sure. I don't get it.
Yeah.
Okay. So in the test, if you're not getting it, you can ask me, and then I'll give the entire class an example. So in this case, an example is, okay, so let's say your data bit is 1 0 1 1 0 0 1 2 3 4 5 6 0. Okay, so 7 bit as your data, right? So in this case, if you count the number of ones, there are 3 ones. 3 mod 2 is 1. So your parity bit is supposed to be a 1. Is that okay? So that's basically how you compute the parity bit. I can give you another example. 1 1 0 0 1 1 0. Okay, 7 bits. So when you look at this, this portion, which is your data portion, how many ones do we have? We got 4 ones. 4 mod 2 is a 0. So the 0 becomes your parity bit. Is that okay? So that's the idea of the parity bit. But the problem is, if you have 2 bits that are received incorrectly, then the parity bit cannot tell you that there's a reception problem. Okay, your 1 bit is not received correctly. So now the second paragraph says, assuming the error rate of a 1 received at a 0 and a 0 received as a 1 are both p, okay, which is sometimes true and other times not true, but in this case we make the assumption that they're both the same, being p, derive the probability of a character transmitted erroneously without being detected by the parity bit. Be sure to show your derivation step by step and quote any theorems used. Okay, so you don't have to recite the entire theorem, you just have to name the theorem, okay, and say that, okay, this theorem is useful to solve this question. All right, so what are we dealing with here? In other words, here we are dealing with a probability. What is the event? What is the omega and what is the event? So those are the things you have to think of first. What kind of outcomes are we talking about? And of all those outcomes, which are the ones that we're interested in?
0 to 7 bits being flipped. And
Okay.
the outcomes we're looking for is pairs or even numbers of bits that are being flipped.
So there are several ways to look at it, okay? Because the problem itself is we know that we are only interested in the cases where there are 2 error bits. The positions of the of 0, 0 is not a problem because we don't have any actual error in that case. 2, 4, 6, or 8. Okay, so all of those we're interested in. Can it be 8? It can be 8. You flip every single bit. Every bit is received incorrectly. I mean, it can happen. You know, the chances is low, but it can happen, right? So now, what does it resemble now? Huh? Binomial distribution. You got it. Okay, so the way we look at this is like this, okay? So you transmit a bit, okay? Transmit. And there are 2 ways you can receive that bit, okay? You can receive the bit correctly. You can also receive the bit incorrectly. Right? Yep.
Are we going to count separately, like whether or not the parity bit catches it, or are we just always assuming the parity bit doesn't catch it?
The parity, okay, if you have 2 bits that are received incorrectly, it doesn't matter where the incorrect bit is. It can be the parity bit, can be the data bits. As long as there are 2 bits received incorrectly, it cannot be caught. Okay, so we know that the probability going this way is p. We know the probability going in this direction is 1 minus p. Okay, does it look like a coin flip to you? It is a coin flip problem. Okay. So when you think about the coin flip problem, it is a binomial distribution kind of issue, okay? So now what we do, okay, we can call this q, right? Q equals to 1 minus p. So now you're basically looking at p plus q, and then the whole thing to the power of 8 because you have 8 bits. You have 8 bits, okay? So we know that this is a useless question to ask because we know it's going to be a 1. So we are not looking at the entire sum. We are looking at some of the entries. In other words, we are only looking at the problems when we're dealing with even powers of q, which means also even powers of p in this case, where q, the power of q is non-zero. Is that okay? So we are looking at, okay, I'm going to leave this one open here. And you guys can tell me later on what it should be. So we are looking at p to the power of 6, q to the power of 2. In other words, we only received 2 out of the 8 bits incorrectly in this case. Next one is we received 4 out of the 8 bits incorrectly. And then the next one is we received 6 bits out of the 8 incorrectly. And then the last one is we received all of the bits incorrectly. Yep.
So are there going to be 2 different things you can put for each one of those, like, binomial coefficients?
Yes, there are 2 ways to specify it because they're symmetric. So in this case, it depends on how you want to count it. You can call this 8.6, 8.4, 8.2, and then 8.0. Or if you prefer, you can also say the first one is 8.2, the second one is still 8.4, the third one is 8.6, and then the last one is 8.8. They'll give you exactly the same number. Okay, so 8.6 is the same thing as 8.2. And then 8.2 is the same thing as 8.6. And the 8.0 is the same thing as 8.8. And that has to do with the equation of the combination. So you can use either set. Okay, so I'm not going to force you guys to associate this number with P or to associate it with Q because it boils down to the same thing. Yep.
Will I be able to use my calculator for those combinations, or will I have to use the formula for them? Can I use my calculator for those combinations, or will
You have to show the formula. Yeah. So you don't actually have to compute the actual value because I'm not giving you what P it really is anyway. So we can just leave it like this, and that would be the answer.
So I don't have to compute those combinations. Like
No, you do not. You can just leave it the way it is. But then you have to explain this as a binomial distribution. So I'm going to write it down here. This is a binomial distribution. So are we good so far? All right. So that's question number 2. This is question number 3. Question number 3 is going to take up a little bit more space, but not too bad. So question number 3 is looking at the omega set when we are dealing with without replacement, and we're only counting permutations. So this one relates to the counting module when we have a generator to generate all the possible permutations from, in this case, we're dealing with an experiment of I trials, and the first trial can have choices coming from T as a set. Okay, so this is really just quoted from the counting module itself. Okay, the equation is not new. So what we want to do is to prove. We want to prove by induction that for any non-empty T, omega the cardinality of omega kt is the same thing as the number of permutations of choosing k out of T, or the cardinality of T. So we want to prove that theorem using proof by induction. All right. So how would you do that? You have to start with the base case. Yep. So we basically say that we select a k first. So this time k is not the induction variable. You have to pick another induction variable in this case. Okay. So we just say that we pick a k. Okay. Select a k. K. And you have to make sure that k is an element from 1 to the cardinality of T. Okay. So as long as it's one of those, we are fine. Okay. Now we want to do this. Okay. So now we want to say make a set. We'll call this U, and U is T minus. So we are basically saying that we have already chosen x many elements, so that U is what is left for the last trial. Is that okay? Okay. Let me change this a little bit. Okay, I'm gonna change the presentation just a little bit. Okay, so we want to choose a set U such that the cardinality of U is the cardinality of T minus, let's see, this has to be the base case.
You want to start with something that has a cardinality like 1 or something? Is the base case?
Yes. No, the cardinality is not 1. We want to work it all the way down to only one trial left. So we start off with k trials to begin with, right? So we want to work it all the way down to one single trial. So that means, huh?
Why not start with omega t then if we're going to start from all of t?
But then you cannot work your way back up to k. So that's the issue. So this is going to be k minus 1. Yep, okay. So we want to make a set U such that the cardinality of U is the cardinality of T minus k minus 1. Okay? And on top of that, U is a subset of T. Is that okay? So now we ask the question, what is the cardinal, what is the big omega? In this case is of 1, because we started off with k, then we move down to k minus 1, then we move down to k minus 2, until we move down to omega 1 of u, and we ask, what is that? Well, according to the recursive definition, if you're down to omega 1, then whatever set is in the parentheses is the set that you get back, right? So now the cardinality of this becomes the cardinality of u, and okay? Is that okay? So I call this the base case. The reason why this is the base case, because when you look at this cardinality, does it match the theorem? In other words, does it really match, we are calculating the number of permutations of choosing 1 out of bar u bar. Okay, this is a question mark. Permutation of choosing 1 out of bar u bar. What do you think? Well, let's expand the equation, right? So the permutation of choosing 1 out of bar u bar, and I'm even giving you, this entire thing here, so you can just kind of plug in the numbers. So now we have u bar factorial divided by bar u bar minus 1, the whole thing factorial. What is that going to give you? It's going to go u bar. Does that make sense? Because bar u bar minus 1 cancels out. Bar u bar minus 2 cancels out. The only one term that appears in the numerator but not in the denominator is bar u bar itself.
After bar u bar on the third line down, is that supposed to be like approximately equal to, or?
No, that's actually equal to.
Oh, okay.
Yep. Is that okay? So now we have the base case proven. So with the base case proven, what is the induction step, and what are we assuming in the induction step? Okay. So we say this is the induction step. Induction step is that the theorem is true for I'm trying to think of an index variable here. Let's say I equals to j, okay? J trials in an experiment, okay? What does that mean? Well, if I say that the theorem is true for j trials in an experiment, then you just kind of plug it into the theorem itself. You basically just say that, oh, okay, so this means the same thing as the cardinality of omega j of some set t, whatever t is. Let's see. I'm just trying to think of whether this t has to be more specific, because we're working with a very specific t to begin with, so I cannot just say that this is true for any t, because I can only use one variable for induction at any particular time. I cannot change multiple things at the same time, so I have to be careful here. So I don't think I can use t in this particular case. I have to be more specific than that. So I'm going to use v here, okay, is going to be, oops, sorry about that, just click on the scroll button here. So I'm just going to say that this is in fact the permutation of bar v bar choose j, but then I have to be more specific about v. So I have to say that your bar v bar is bar t bar minus k, let's see, this is j trials. I'm thinking about the indexing here. So we are working from 1 up. So we got 1, 2. How many elements will be missing in V compared to T? So when J gets closer, sorry? Yeah, because when J is larger, which means we have more trials remaining, we want V to have more elements. So, oh, okay, I know what it is. Okay, so it's going to be, the other way to put this is U plus, because when we're down to U, we only got one trial left. So that means, this is J minus 1 here. And then we also want to make sure that V is a proper subset of T. There we go. So we are working our way back up. That's the whole idea. Is that okay? Yes? No? Are we good? We don't know. Okay, so we'll just kind of move ahead like this, because what we're doing is we're looking at this one as a base case when we have only one trial left. So when we have one trial left, the set that we can choose from is going to be bar t bar minus k minus 1 in parentheses. This is how much choices we have left when we get down to the last trial of the entire experiment.
The very end right there, is that bar v bar negates J?
Where?
On the very right.
Negate?
On the right, yeah. Closest to you.
You mean
No.
on the right?
Right.
Uh-huh.
There you go. That's right where your pen is.
Where?
Right where your pen is. Is it a comma? Yeah.
This one?
Yeah.
Yeah, that's comma.
Okay.
Yep. It's the permutation of choosing J from bar v bar. Is that still okay? All right. So this is our assumption. So now the question is, assuming that this is true, what about omega j plus 1? So when we're talking about omega j plus 1, then we have to choose from V union with something that is not original in V. So we'll just call that E here, where E does not belong to, it's not in V, okay? But E is in T. Is that okay? We're just adding one more element back to V to make it bigger, one element bigger. Is that okay?
Can you read what it says after omega j plus 1?
Huh?
At the very bottom.
Oh, this is omega j plus 1. So we have we have j plus 1 trials for this particular sub-experiment. And then in here we have V. This is union. Yeah, it's union with E. So we're adding one element to V. But I cannot say add an element. We can only use union as a set operation. Okay. So now when you look at this, what is that going to look like? Well, we use the definition. So we basically use this particular definition and apply it back here. But when you look at that definition, big U, and I cannot use E again. I'm going to use F here. And this is T minus E. So it's going to be V union with E, and then the whole thing minus the set of F, like so. Are we good so far? Okay, so the first question is, since I'm doing a union of a bunch of Cartesian products, so the question is, do they overlap? Is there any chance that they can overlap? Is there any overlapping that I have to worry about? If you look at the first one, if you look at all of these sets generated by these Cartesian products, can they possibly have any overlap? Which starts with the question of what is inside these Cartesian products? They have tuples, right? So now the question is, can they start with the same element? Because if they cannot start with the same element, they cannot have overlaps. Yep, so they cannot overlap. Okay, so if they cannot overlap, then the cardinality of each of these terms would be the same, and we just have to multiply how many terms we have here by how many items is in each of these sets before we union. That will become the total number of sets that we are dealing with after this generation. Is that okay? Is that okay so far? So now I'm going to... They cannot overlap.
Okay.
There cannot be any overlap. So now we put cardinality on top of, on both sides here. Okay? So now we ask this question is, how many elements do we have in T? Well, it's the cardinality of T, right? Oh, I take it back. This is wrong again. Sorry about that. This is V unioned with the element of E. So this has to be the same thing. V unioned with the element of E times, this is a arithmetic multiplication to each of these, the cardinality of each of these omega j V union with E minus F.
Can you read that again from the beginning?
Which? You mean this part here?
Yeah.
It's V union with E minus F, which is the same as that. Huh?
From the equal sign.
From the equal sign? From here?
Yeah.
Okay. This is the cardinality of V union with the set of E, and this is the end of the first cardinality operator. Okay, let me move it up a little bit.
Okay.
Here we go.
The cardinality of V.
This is the cardinality of V union with the set of E, and an end cardinality operator. This is arithmetic multiplication. It's just arithmetic multiplication. This is cardinality begin, omega j, open paren, and then we have V union with the set of E minus the set of F, close paren, and then close cardinality. Okay, so now we look at the assumption. We look at the induction step assumption. It says that we assume that the theorem is true for this already. Okay, but it's the cardinality that matters. So when you look at the cardinality of this, it matches the cardinality of that, because E and F cannot be the same. Oh, they can be the same, but E cannot be in V. So V union with E would yield a cardinality of the cardinality of V plus 1. And then since we subtract 1 from it, so now it's 1 fewer. Is that okay? Okay, so let me see if I can convince you of this now. V union with E. Can I convince you that this is P, or the number of permutations of choosing J from the cardinality of V? Can I convince you of that? Yes or no? Does it match? Okay, does this thing here match our induction assumption, which is this? The cardinality of V, the cardinality of omega j of V is choosing J of the cardinality of V. That's our assumption. So the restriction of this V is V is the cardinality of V is the cardinality of U plus J plus 1, and then V has to be a subset of T. That's the only restriction. Yep.
So like, is it just that if P and F are the same, you're adding in an element to V and then taking out
Yeah.
that same element, but if they're not the same, you're still adding in an element and taking that out, so you still get that
Yep.
V has the same amount of elements as our induction step?
Yep.
So,
Yep. Exactly.
okay.
So did everybody hear that argument? Yep. Okay. All right. So are we still good with this step here? Translating this cardinality into something that our induction assumption has already talked about. Is that good? Okay. So the next step is just to work out what is the cardinality of V union with E. What do you think? Yep.
Is it just going to be the cardinality of V plus 1, so will that be our, like, K plus 1?
Yep. So we have V plus 1, the whole thing, times P of V, the cardinality of V, and choose J out of it. Are we good so far? Now, how do we know that E is not in V? The element E is not in V. Because you were told. Yeah, the strikeout means it is not. Or if you choose, you can say you can put a negation, and then just use the normal element of. Yep.
When we get to like expanding those out, what are we going to be looking for in terms of like comparing it to our assumption? Like, are we going to look for V plus 1 factorial over V factorial? What are we hoping to get at the end?
I mean, you mean the next step of the derivation?
Sure.
Yep, we can go for the next step. Okay, so we'll look at the next step of the derivation, which is basically just working with numbers. We're done with working with sets, right? So now we expand what is the permutation of choosing J out of bar V bar. So by definition of permutation, it will look like this, right? So the permutation definition is up here. So we're going to do, right? Oh, factorial, of course. Almost forgot about that. Yes. So are we doing okay so far with this? Bar V bar factorial divided by bar V bar minus J, the whole thing factorial, is the number of permutations of choosing J out of bar V bar. Because that's just the definition of permutation. So now we have this extra multiplication of a bar V bar plus 1. So now the top becomes var B var plus 1, the whole thing factorial. And then we have to, and then the bottom has to be, the bottom is the same, which is not cool. Because we want the bottom to also have that plus 1.
We
Yep.
change where we define V to be like U plus J.
Yeah, you can do that. But I'm still missing the bottom part. The denominator has to be bar V bar plus 1 minus J, the whole thing factorial. So I'm missing the plus 1 somewhere. Because the way it is right now is we only got bar V bar minus J, and then the whole thing factorial. I'm missing the plus 1. I'm kind of stuck here. Okay, we got 2 more classes to go over this one, so I'm going to have to figure this one out. But I'm fairly sure, all the derivation up to this point, this part translating to this part here is correct. This part translating to this part should still be correct. So I'm missing something about the denominator somewhere along the line. Okay, so we'll get back to this one. Question number 4. Proof by contradiction that the following is true for all integers. X, being an integer in Z. If x squared is even, then x has to be even. So I want you to prove it by contradiction. So this one is not about resolution. It's not about CNF. So don't even try to solve it by CNF and resolution. This is just a general proof by contradiction problem. Kind of like the pigeonhole principle. Okay, so I'm just testing whether you guys know how to apply proof by contradiction. So how do you prove by contradiction? You first have to identify what? The theorem or the proposed theorem. Okay, so in this case, what is the proposed theorem? Exactly. So this is our theorem. Okay. All right, so if that is our theorem, what is the first thing we need to do when we are trying to prove by contradiction? Negate our theorem, okay? So you say the negation of the theorem is, now since I'm not using formal quantifiers, well, I am, but you don't have to, okay? So the quantifier is saying for all, x in an integer, this is true, but what we are going to do is just to say it is not true. It's the opposite of x squared is even implies x is even. Does it work? So I'm converting the sentence, if x squared is even, then x is even, into, kind of like a semi-English and semi-mathematical equation. I could have done the whole thing using the mod and the comparison operation to say that it's even, but this suffices. Okay, this is enough. Okay, so now we have a negation on the outside, and then we have not x squared is even, or x is even. And where does that come from? We're removing the implication. Okay. So, let's make it easier to understand. So we can say it is not the case that x squared is odd or x is even. Is that okay? Because I'm just negating, I'm putting the negation not here to is even. Well, if a number is not even, it is odd. Okay, so I'm just converting that part. So it's easier to read. So now I apply the negation on the outside using Demorgan's law to stuff in the inside. I'm distributing the negation into the inside. So now it becomes x squared is even and x is odd. Does it make sense? I mean, so far I have not done anything in algebra. This is all Boolean algebra, not algebra. Is that okay? All right. So now you have to say, well, is that going to cause me a problem? Is this a contradiction? We have x squared being even and x is odd. Why is that a problem? Yep.
You just check it by squaring x is odd and squaring 2x plus 1, I think, or 2b plus 1, we should get
Yep.
odd.
Okay. So well, if x is odd, then x plus 1 should be even, right?
What I mean is, like, if we take x and we say
Mm-hmm.
x equals like 2b plus 1 for some b,
Mm-hmm.
square it, and we have to square 2b plus 1, and then at the end we should get an even number if we don't want contradiction, but it means we get an odd number again.
I'm gonna
What's wrong?
close the door. They're running a leaf blower right across on the other side. Something about maintenance today. Okay, so if you get to this point and you say this is contradictory, I will count it as 100% already. I mean, if you want to prove this further and say that, okay, I'm going to use algebra to prove that if x is odd, then x squared cannot be even, that's fine too. But that kind of goes back to the question itself, right? You do not see a contradiction here? Why, this has to be false? Okay, well, let's see here. So we can first go for a few examples, okay? So we say x is 3, x squared is 9. So they're both odd. Not one is even, one is odd, right? X equals to 4, x squared is 16. They're both even, okay? So now the question is, how do we know that x is even and x is odd is a contradiction? And this one, you have to use arithmetic algebra. You have to use actual math to do it. You square x plus 1. 2v plus 1.
If x is odd, then it equals 2v plus 1.
Right. Okay. Huh? Okay. So now we can say if x is odd, then x equals to 2n plus 1, where n is in natural number. Right? Is that okay? Does that make sense? Then, huh? We're trying to show the contradiction that we're trying to show that this implies false. We need to show that. Okay. But first of all, can we say that if x is odd, then x can be expressed as 2n plus 1, where n is a natural number? Okay. So now what happens to x squared? X squared is 2n plus 1, the whole thing squared, right? Which is going to be 4n squared plus 4n plus 1. I think so. Yep. Okay. So now, when you look at 4n squared, so n squared itself can be anything. It can be odd, can be even, but 4 times that thing is going to be even, right? So now we have an even number. And then what about 4n? Say, okay. Yeah, it doesn't matter what n is. N can be odd or even, but a multiple of any multiple of 4 is even. Can we establish that? Yes? Okay. So it doesn't matter what n squared is. It can be odd, can be even, can be 0, but 4n squared is going to be even for sure. 4n, same thing. I don't care what n is. Can be 0, can be 1, can be 5, can be 6, but 4n itself has to be even. Yep?
Can't we state that any even number times an odd number creates an even number, an even result?
But we don't even need that. Because now we have even number plus 1. And this is even, right? So we have an even number plus 1, and this has to be odd. So we have just shown that x squared has to be odd. But wait, it's also saying here the inverted or the negative theorem says that x squared is even. So now we have a contradiction. A number a is even if and only if it can be expressed as 2 times b plus 1, and b has to be an integer or natural number. Depends on whether you allow negative numbers. Yep, question?
Do you have to restrict that to not the natural numbers, but the positive? Do you guys do that?
Say that one time.
Don't you have to restrict that to positive numbers, not natural?
Well, negative numbers can be even too. because this part here is only using integers. X can be positive or negative.
But I mean, you have for n in the natural numbers, right?
For n being a natural number. Oh, you mean here?
Yeah.
Yeah, this part can be we can use z here.
Yeah.
Yep. But it still works the same way, because -2 is still even, -4 is still even.
But if you had n is 0, and you have x is 1, and
Yes.
square is also 1, right? And 1 is odd.
Say that one more time.
If you have n is 0.
N is 0, okay.
Yeah.
So if n is 0, then x is 1, right?
And x squared would also be 1, right?
Yes. And it's not a problem, because we know, from arithmetic algebra, we know 1 is odd. But the theorem says x squared 1 is even. And that's where we have our contradiction. Because you cannot have a number that is both even and odd at the same time. So when the inverted theorem says x squared is odd, but you're using derivation, you say x squared is odd, then you have a contradiction, because it cannot be both. Is that okay so far? Okay. And this is question out of 5. You guys will like this one. Assume that tech plays the League of Legends, and there are 612 players. Of these players, 106 are so salty that tech does not want to team up with. So each team has 5 people. What are the chances that tech teams up with a team with up to 2 undesirable, too salty teammates? Explain your reasoning and why you use the formula. Okay. So what is the general pool? Okay, the pool is 612, right? Okay, so we got 612 here. And within the 612, we have 2 categories, and they do not overlap. Okay, the ones that are salty and the ones that are not salty, or below or above a threshold, right? So we have 106 that are too salty, and the rest are acceptable. Okay, so we have 612. Okay, we'll just say this is 612 minus 106. 500 what?
506.
506. Okay. All right. So now the question is, what are the chances that tech can end up with a team with 2 undesirable, being too salty, teammates? Okay. A team has 5 people, right? So I want to choose 3 out of. Oops. The other way around. Choose 2 out of here, and choose 3 out of here. So we have 106, choose 2, and 506, choose 3. Now, that is not the answer, okay? It's part of the answer, but it's not the answer. Because the question is not asking how many ways can tech team up with 2 teammates who are too salty. If that were the question, this would have been the perfect answer. But that was not the question. So this will give you, okay, if you multiply these 2, it will give you the total number of ways that tech can team up with 2 people out of 612 that are too salty. But then we have to divide it by omega. We have to divide it by the total number of ways that tech can team up with people in the whole team. Now, of course, there's one problem here. Because since tech is a part of the team, we only got 2 more people to choose from. So we also have to assume that tech is not one of these 106 people, right? Yep.
For League of Legends, I feel like the ratio should have flipped around. 506 salty players and 160 normal nice players.
Well, there's different concentrations of saltiness. Okay, so now the question is, what do we need to divide the whole thing by? Okay, we have to divide it by the total number of choosing 4 additional teammates out of 612 people. So that would be 612, choose 4.
That's omega.
Hmm?
Is that omega?
that is the cardinality of omega. So this part here is the cardinality of omega. Is that okay? And that's the answer of question number 5. Sorry? So are we okay so far? Yep. Say that one more time. Why is it 4 and not 6? Because I'm one of the players already. So a team has 5 people. I have to choose 4 additional teammates, right? So now the question is, of the 4 additional people that I'm choosing out of 612, what are the chances that I will choose 2 who are too salty? Yep. Yep.
This answer is for exactly 2 salty teammates, and it's
Yep.
the question up to 2. Does that change?
Oh, up to 2. Okay, so we have to also include a 1. Yep, we have to add the 1 too. So you're correct. So the correct answer is you have to add 106, choose 1, times 506, choose 3 in that case. Because up to 2 undesirable teammates, and then also the 0. So we have 106, choose 0, times 506, choose 4. So the numerator will become this sum here with 3 terms, because I might be lucky, I don't get anyone salty in my team. That would meet the requirement of up to 2 undesirable teammates, because 0 is less than or equal to 2. I might have 1 single teammate who is too salty, or I might actually reach the maximum, which is 2 out of those 2 undesirable teammates. So you're correct. So you have to sum all of those, and then you divide it by 612 divided choose 4. All right. Yep, question? Yes, that's a choose 0. Because I might get lucky and have no one in the team who is salty. If I have no one who's salty in the team, it still meets the requirement of up to 2 undesirable teammates before I rage quit. So you can basically look at this and go like, what are the chances that Tech will just turn off his computer, right? Unplug it. I met a person who actually did that in the middle of a League of Legends game. He just got so pissed off. He reached for the power cord. He did not even bother to push the button or properly shut down the computer. He just reached for the power cord and go. And then a few minutes later, he plugged it back on and was scrambling to get back into the game. I think it was a ranked game. That was why. So are we good so far with this test? There's only one question that I kind of need to work out the math again, because I thought I got it figured out, and then they go like, no, we're missing that 1. So I have to figure that out. So do you guys know how to prepare for the test? Okay, so this is how. Okay, I'm gonna put this back up here. All right, so you have to kind of think about what kind of stuff is in the test. So there are a few main categories. So I'm going to use a text editor here to help explain what you guys can do to prepare for the test. So the first one would be CNF stuff. Okay, so when we talk about the CNF stuff, there are a few subcategories. So we have Boolean, expression, converting, to CNF. Okay, that's your first homework assignment. I gave you a Boolean expression, and you have to turn it into a conjunctive normal form. So you have to remember how to do that. The second one is proof by contradiction, which involves negating the theorem. Okay, but the negated theorem you also have to turn it into CNF. Okay? And then the last step is resolution. So the resolution part has a few sub-steps as well. So you have, okay, we'll call this psi CNF. CN. So you have to look at psi CNF and negated theorem CNF. Okay? So you have to put those two together, and then you perform resolution. Perform resolution until one of these two things happens. One is you reach contradiction. Contradiction is reached. Then you can stop, because you can then conclude that the proposed theorem is actually a theorem. Or impossible to make new terms. So you have already done all the possible resolutions, but you cannot get to the contradiction. So if you get to the second one, like you cannot reach contradiction, but there's no additional resolution to be done, then you have to come to the conclusion that the proposed theorem is not a theorem. So are we okay so far with the CNF stuff? Is that okay? The second part has to do with discrete probability. So discrete probability is broken up into a few things. The first part is counting. So counting involves the concept of an experiment. Okay, an experiment is a series of trials. Okay, and then you have a few categories under this. Sometimes we are concerned about permutations. Other times we're concerned about combinations. Are we good so far? Under permutations, we have two subcategories. We have with replacement, which is a coin flip problem, okay, or throwing a dice. Okay, those are all permutation problems with replacement. But we can also have permutations without replacement, which is like just choosing something out of X many things, but you cannot make the same choice again. That's without replacement. So in this case, this is what the permute function, is for computing this. With replacement, it's just a power function. Then we have combination, where ordering does not matter, like the lotto game. So this is always without replacement, and we use the combin formula in a spreadsheet. So are we good so far with all of this? Okay. So within the experiments, we have one special type of experiment. Okay. So special case is experiment with replacement, but only 2 outcomes per trial. Okay. So that is the special one, because now it becomes binomial distribution. So this is binomial distribution. So are we okay so far? Now with binomial distribution, you can also have probability associated uneven. Okay, so we can actually deal with tilted probability distribution across the 2 outcomes. The other ones we assume it's the same. So when we are talking about the lotto game, we're not assuming that we can handle the case when those balls can weigh differently. Does that make sense? Okay. But when we are talking about coin flips, binomial distribution allows us to deal with a case when the coin is loaded. So the chances of landing on the head and the chances of landing on the tail can be different, and the binomial distribution can deal with that. Is that okay? And then we got 2 proof techniques. we have proof by contradiction. So when you're dealing with proof by contradiction, what you need to do is to first identify the theorem. Then you need to negate the theorem. And then you want to see if the negated theorem leads to contradiction. If so, the proposed theorem is a theorem. If not, the proposed theorem is not a theorem. Is that okay? So the example of proof by contradiction is the square one that we did today, and also the pigeonhole problem that we talked about in class. So both of those are examples of how to prove by contradiction. Another proof technique that we talked about is proof by induction. So with proof by induction, the first thing you need to do is to identify some kind of recursive definition. The next one is to identify the base case. Okay, so the base case is always working with a concrete number applied to the theorem. So the theorem typically, when you need to prove by induction, the theorem itself says, okay, this blah 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 is true for all n, where n goes from here to some end. Okay, can be infinite on one side, can be infinite on both sides. So the base case is basically just saying when n equals to 0, we can prove the theorem is true. Okay, and then you have to work on the induction step. The induction step has two distinct components. The first one is the induction assumption, which basically states, let's just assume the theorem is true, but only when k equals to k, when n equals to k. That's usually what the induction assumption would look like. Then you have the induction step proof. So now you have to prove that the theorem is also true for n equals to k plus 1, assuming that your induction is going on the positive direction. But your induction can go in the negative direction as well, which means you can also say that n equals to k minus 1 if you're going in the negative direction. Okay? So I think that pretty much sums up, the scope of exam 2. Are there any questions? Oh, a few more things. Are we out of time? We are kind of out of time. Okay. So you might want to study a little bit of algebra related to factorial. Okay, just because factorial is kind of special, there are certain tricks you can do with factorial that you otherwise cannot do with normal math. Or, there are ways to simplify and ways to expand things. All right, I'll see you guys on Wednesday. So unless I tell you otherwise, we're going to go back to the other classroom with all the uncomfortable chairs.